Hi everyone, we're continuing with Riemann sums, and now we're going to talk about the definition of a definite integral. So what we've done so far is we've taken like some curve, okay, and what we know how to do right now is we can split this up. So over some interval, okay, I can split this up into however many intervals I want. We've done 4 usually, and I can find the area of this using rectangles. So at some, we'll call it k. K is just a placeholder in this case. So at some kth interval, I can make like a left Riemann sum or a right Riemann sum or a midpoint. That gives me some rectangle. I can find the area of that rectangle. I add all of them up. I get an estimate of the overall area under the curve. And now we've already talked about how most of the time it's going to be an over and under estimate depending on what kind of Riemann sum you're doing. And so we want to do a better job. So we can do that by using a definite integral. So here's what we know. Okay, we know that the area of a rectangle is, well, I'm going to write it kind of in a specific way. I'm going to say that f of c sub k times delta x is the area of my rectangle. Okay, now this is written a little bit weird. All that we define c sub k to be is some x value. Okay, so this is just a placeholder. This tells me which x value I'm talking about. Like the first, the second, the third, that's it. Right? And f of indicates that this is a y value. So this is like the height of my rectangle. Delta x is just the width of my rectangle. Okay, so height times width or length times width, whatever you want to call it. This is just the area of a rectangle. You've already known how to do that. Okay, now if I want to add all the rectangles together, we can use a sum. So we use sigma. Okay, we start with the first one. Okay, so k equals 1, and I go till n. So however many intervals I want, I start at the first interval, I end at the nth interval. And then I'm just going to put the area of a rectangle on the inside. So again, like this is my width, this is my height, same thing. Okay, and this is what we call a Riemann sum. So this is what we've done so far. Okay, now what if we want to do a better job? Well, the idea that you kind of notice is that the more rectangles we have, the better our estimate is. So we can think about this in 2 ways. Okay, we can think about the number of rectangles we have approaching infinity. Okay, so more rectangles is better. Or we can think about it as the width of my rectangles approaching 0. So the more rectangles I have, the smaller the width of each rectangle gets. And so either way of thinking about this is fine. And so we get to the idea of taking the limit. So if I can take the limit as n approaches infinity of my Riemann sum, so starting at 1 to n f of c sub k times delta x. Okay, so if I take the limit of this as n approaches infinity, I'm taking the area of an infinite number of rectangles, adding them all together, which is kind of weird, but you know, it works, and that will give me the exact area under the curve. Okay, I just go to infinity in this case. And so we're given the definition of a definite integral here, and that's where that comes into play. Now let's talk about notation real quick. Okay, this squiggly here is an integral that's telling me to find the area from a to b. So I always go from bottom to top. A is my first bound, b is my second bound of my function. Dx tells me with respect to x. You can kind of think about dx and delta x are very similar notation-wise. So dx tells me what I'm integrating with respect to. F of x is my function, integral from a to b. Okay, and that's the same thing as what we just talked about. Okay, an infinite Riemann sum, essentially. A Riemann sum going to infinity of my areas. Or over here, we're thinking about this as the width of each of my rectangles approaching 0. All right, so let's move on to actually doing some examples and talking about properties. All right, so the properties of my integrals are pretty similar to what we did with limits earlier. All right, so first, here I have an integral from a to a. Okay, this is a rectangle with a width of 0. Right, so that's like a line. So a line has an area of 0. Okay, so a width of 0, length times width, you get 0. Okay, this time, instead of going from a to b, I'm going from b to a. So direction does matter when you're taking an integral. You want to be going forwards, it's positive. If you're going backwards, that's negative. In this case, I'm going from b to a, I'm going backwards. So that would give me a negative area. You can have a negative area. And so this is the equivalent of negative a to b of f of x dx. Right? And if you're confused about why you can have a negative area, remember that we're finding the area under a rate. And so you could think about that as like a loss or something like that. Okay, here I have a constant in front of my function. And so just like with limits, you can bring constants out of your integral. Okay, and so this is saying that if you have some graph from a to b, okay, if you pick some c value in the middle, okay, you can find the area from a to c and then from c to b, and that'll be the same thing as the total area. So you can pick some point in the middle. So a to c, and then from c to b, and that'll give us the same area as just from a to b. But sometimes it is beneficial to pick a middle point. Okay, if you're adding two functions together, you can split them into two totally separate integrals. Right, and same thing if you're subtracting. Right, now there's no like special product rule or quotient rule for integrals, so we're gonna have to do something else with those. Right, so let's actually go through some examples. Right, so we're just gonna do these geometrically, because remember, we are just finding area after all. So first, I'm finding the integral from 1 to 6 of 4. So 4 is my function. We know that that's just a straight line from 1 to 6. So here's the area that I'm finding. Okay, between 1 and 6, my function is 4. I have a rectangle. Right, so I have a width of 5 and a height of 4. So 5 times 4 is 20. And that's the area. That's it. Alright, next example, I have a linear function starting at 2, slope of 1, it increases from 1 to 3. Alright, so here is my graph, here's my area, and so I see I have a trapezoid here. And so we find the area of a trapezoid by just averaging my bases. So my first base here is going to be 3. My next base is 5. I'm getting these heights just by plugging my x values into my function. Okay, I'm going to average these and then multiply by my my height, or in this case, my base length, which is 2. So I end up getting 8 for my area. All right, so that's just the area of a trapezoid. Okay, next one. Hopefully you recognize this is a semicircle with a radius of 2. Right, and I'm finding the area between -2 and 2, so that works out real nice. Right, this is a semicircle because it's not plus or minus. Okay, so you find the area of a circle by doing pi r squared, but it's a semicircle, so we're going to divide it by 2. I have a radius of 2. So 2 squared over 2, so that's going to give me an area of 2 pi. Right, and then last one, I have a bunch of triangles. Now, the one thing to note about this example is that I have some triangles under the x-axis. And so I'm going to have a negative height for these because I'm going under the x-axis, which means that, again, I'm going to have a negative area. Right, so for this triangle, I have a height of -2 and a base of 3. So I'm going to have an area of -3. Okay, here I have a height of 3 and a base of 3, so my area is 9/2. And then here I have a base of 2 and a height of -1, so I have an area of -1. So I'm just going to add all these together. So -3 plus 9/2 minus 1, that gives me an area of 1/2. Right, and again, if you're confused about having negative area, just imagine like this function represents, I don't know, how much money you're making, right? So if if the amount of money you're making nets in a negative area, that means that you lost money. Right? That's just what that means. If you're above the x-axis, that means that you gained money. Something like that. Right, so just keep in mind that these are all rates, and we're finding the area under a rate. All right, last example. So given this information, they want me to find some of this stuff. All right, so here I know the area from 0 to 3 is 4, and then from 3 to 7 is negative 1. They want me to find the area from 0 to 7, so I can just add these together. Okay, the area from 0 to 7 will be the same as the area from 0 to 3, and then from 3 to 7. So that's going to be 3. Okay, here I have, again, a rectangle with a width of 0. And then here I have a constant. So again, I can bring this 2 out, or just think about this as 2 times the area from 3 to 7. So 2 times the area from 3 to 7, which is negative 1. So that's going to be negative 2. All right, that's it for this video. See you all later.